Hey, hello. I guess this is part two to FSAE STAR-CCM tutorial. Let me close that really quickly. Nope. Okay, so pretty much last time I talked to you all about basic external flow, and this time I'm going to talk to you about the full car and how it's different for the full car. Sorry. So first, where I actually want to go is not based on the full car. It's a completely redone slash um, new post-processing package that includes pretty much more, and more is better. So as you can see, you can go to scene plot. Here are all our types of post-processing, all in one scene, which is quite good. Tops that there's new stuff here, so that's also good. Pretty much everything that you would get with the Chris Penny tutorial, minus I think one thing, which is not that useful. But as you can see, this is the full car. Front wing, rear wing, basic designs, not special anyway. But essentially, I have geometry open. I can double click that and make it go away, and then I can bring up something else like coefficient of total pressure planes, and go through and go here and look at all of them. I think I went through planes last time as we do post processing. One of the most in-depth ways of making processing. Of course, there are others. Those ways are also very important. But yeah, let's pretty much go through what each of these does. So this is the planes. Well, that's coefficient of pressure planes. I go pressure because of the nose cone. Let me get rid of this, get rid of that. Then let's skip over flow separation really quickly. This is the pressure geometry. We saw this last one as well. You have high pressure and low pressure on the geometry. You have a scale here that tells you what's what. And you look at the geometry, high pressure, low pressure. Very useful. Very useful for comparing designs to other designs. You can look at the low pressure, like, that's where we're gaining and losing downforce. But I went through this last time. This is a kind of review. And so are the planes. I went through the planes last time. But the new stuff. Let's get to the new stuff. Okay, let's open up the geometry. And first, there are two new isosurfaces. We looked at TKE last time, turbulent kinetic energy, pretty much what it is, turbulent kinetic energy. We looked at, where is it? Q criterion. If that's going to work, there we go. There it is. We looked at this last one as well. Where are vortexes? Where are they, fading in and fading out? Vortex, vortex, vortex. Of course, these new ones are something very interesting. Now, the first one is called static pressure. This is going to show, okay, well, we need geometry too. Make it make sense. This is where our static pressure is, where we're going to have a lot of high pressure. And it just shows you that above a certain number. And as you can see, you can go into derived parts, isosurface, everything, in their groups. There are, of course, these values that you have to set to get reasonable results. Here is 50 pascals, and for total pressure, which we'll see soon, -1. Same values that are in the Chris Penny simulation. However, pretty much you're getting everything from that except, it's custom and it's easier to use in less space. Generally, it's better. Static pressure. Let's go to flow separation. This comes from this other one, total pressure, which just shows you where the flow is separated. And as you can see behind tires, pretty simple stuff. Behind the car, that kind of stuff. These two are useful, but I would say not that useful. I would say that this is pretty useful for seeing where the pressure buildup is, of course, under the tires. But you can see that the front wing is definitely helping, because look at the static here versus static here. You can look at these things, visualize these things. Obviously, on the rear wing, that's going to show you where a lot of the drag is from. But the rest is more interesting. This is kind of like let me show you the rest. First off, streamlines. Now, how streamlines are done here is you go up in streamlines, you make a grid, essentially a grid that has a bunch of, like that. You zoom in, bunch of points. Now, how you do this is you go to right parts, new part, probe, presentation grid right here. Pretty much come in and you'd resize your grid, you'd resolution higher, lower, yada yada. You make your grid, and then from that you can seed streamlines from the grid. I don't know what happened there. Well, that's just not good. But as you can see, you have other things. Boom. There's rear wing. This is pretty cool. Let's go to, yeah, this is our grid here. So essentially that's what it is. And what you can do with this pretty much is separate where the air is going and get a lot of useful information from the flow. So let's just go and look at that. It's all under the streamlines right here. So right now we click to open it. This is all just the front wing right side. So we can look where is the flow going? You know, flow is coming up here, flowing over here, flow is going this way, and you can really see, you know, what flow is going under, how much turbulent flow, you know, there is some turbulent flow in the floor. Of course, look at all this. I also, you know, hide show. Now you can see this. All these streamlines, see where these end up eventually. They end up, you know, a lot on the front wing, so under the rear wing eventually, and you pretty much map how the front wing affects the rear wing, how the front wing affects the floor. You know, you got the turbulent flow coming in here, all sorts of good stuff. And you can just, I've seen people, high level people do this and really gain a lot of information from these streamlines. There, we already saw that. Let's do duct. We can look at the duct. It's going to give us a lot of information about, you know, how much turbulent flow is ending up in the duct. Of course, we can do this from planes as well, but no, this is just a lot easier to visualize, and you can see it in 3 dimensions really. Of course, one that is also very interesting, which you really can't see, is this. You know, wait, where is it? Where? Yeah, this one is the one. Pretty much, yeah. What air coming from the side and being kind of just pulled in, and all of it ends up with your wing, which is interesting. You won't be able to get this kind of information from a section plane or any sort of isosurface. So Streamline's very useful. You have to set them up. These are all set up for you, but very useful stuff. Now finally, the final thing which I think is very useful is here, oil streaks. We get rid of geometry. What this does is, I'm going to show you how to do this actually. How to figure this out. What you want here is, where is it? Cell relative velocity. If you put velocity, regular velocity, what you're going to get is this blue. And of course, tires spin, you know, velocity right there is going to have speed. Gee, this is boring. This is nothing. It's the velocity on the geometry. But if you do cell relative velocity, you can see, you know, all the, well, the streamlines on the surface of the geometry. Now this is especially useful when you're trying to map out, you know, small points of separation. Maybe there's separation like right here, and your streamlines are right over here and right, you know, in front of it and behind it, but you can't actually see separation. Or you're wondering why there's different low pressure there. You can look at this and be like, is it separating? You know, there, separation right there. Easy to find, a lot easier than, you know, looking at other stuff. Separation, yeah, stuff's going on over there. Separation here. Of course, you'll find that also in planes, but separation, something's going on over here as well. You can see that. That's a problem. Overall, you can see these things and visualize these things very easily, and that's what oil streak's really good at. Also looks awesome. But enough about that. Enough about the post processing. I think we've gone through the post processing. Let's get back to geometry, and let's go into why this essentially is different from the regular car. And there are two main reasons. First is reports. You're gonna have much more reports than if you just did a front wing and a tire. You have, of course, downforce, drag, downforce, drag for each large element. Now, the crisp penny simulation does downforce drag for each element. I find this to be not very useful because, I mean, these elements right here, if you know what you're talking about, they are a team. They work together. Knowing downforce of this element and then this element, not useful, but knowing how they work together to make downforce, very useful, which is why I have the entire front wing, essentially, as one part. separating these just gives us, information that's not useful, and then we have to add it up to get the actual drag numbers or downforce numbers. So there's a large scale downforce drag, from downforce from drag. If you want to get depth, what actually is causing, inspiration, use oil streaks, use pressure, use section planes. That's what that's for, really. You just want to know the full numbers, compare the numbers from another design. Here are the full numbers. You don't have to do any adding. They're right there. You click on them, downforce. Easy. Of course, there's another thing that's called the COP. Now, this is all brought in from STAR-CCM simulation. And what it's telling you is this, the center of pressure of the car. Let's go to side. Where in the x-axis is the aerodynamic pressure? How much on the front, how much on the rear? Just, yeah, generally what it is. Front tire, 45%. Rear tire. Okay, let me click this. There we go, going down, 54%. Pretty simple stuff. This does all the calculation for you. This can all be found in the STAR-CCM simulation, which I will have linked in the description. But yeah, I just copy this over, copy all the geometries in, and yeah, life is good. Now, the final thing is actually not here. Final thing is not here. Final thing I'm actually going to go somewhere else to show you, different simulation, and it's the idea of, yeah, it's not even here at all. Let's go and load a new simulation. Browse. Let's go to my personal files and look for full car template. Now this one has 3 different regions. As you can see, this one has 1 region. And your question is, why would I need 2 different regions? The main reason for that is, we will wait as it loads. The main reason for that is to have a radiator / fan. That's essentially the only reason. And how to do this is actually found under STAR-CCM. You can find it under STAR-CCM help. It's this button. Search in fan radiator, yada yada. But I'm going to go through pretty much basically how to do it. Let's go to full car template. And let's go to regions. As you see, fan radiator. So what's going to happen is, fan has the boundaries: fan downstream, fan upstream, fan shroud, which is what's around the fan, and then radiator to fan, if you have the fan and radiator connected, and then fan upstream. So essentially, the fan right here, let's say your radiator right here, you have sideball. If your fan's right, let me go back to fan upstream, downstream is pretty simple. Fan shroud will be the kind of the outline of the fan, and then fan to radiator will be the fan and the radiator connected. Now you're saying this, what is this? This is called an interface. It'll show up here when you make one. Now, essentially what I do is here's radiator. When you have multiple regions, you need to interface the faces of the regions. So if you look at subtract, you have the same thing, radiator downstream, and you'll select the same thing, select the same geometry. You'll select the same geometry, or okay, you'll select the subtract side of the geometry, in which subtract off a geometry with a radiator downstream and upstream, and then pretty much radiator will be a box you place in there. And when those faces connect, you'll have radiator upstream, radiator downstream. What you can do to make this interface is you go here, here, nope, that's wrong. Here, you right click, create interface, and then what will happen is down here you'll have interfaces, and you can select your type of interface: fan, battle, radiator, all this stuff. This is all outlined how to do all of this pretty much in STAR-CCM documentation down here at the help button. Very important. Of course, we won't actually put you there, but who cares? And essentially what will happen is you can then set values for the region. So radiator is a different kind of region. As you see, it's dark blue, it's a porous region. All you have to do is come here, fluid region, porous region. Very simple. Fan is also fluid region. But what you can do, I believe, boom, that's not there. But yes, there's a way to set the fan speed, and it will appear. You'll get a fan table from the provider of the fan, and where is it? You go to tables. You'll input it here. You get a new table. You'll input the table there, and you'll link it to the fan. This is all in documentation. I will not do this, but essentially, I'm just explaining how to use multiple regions, create multiple geometries, create a geometry that represents the radiator. It's just a box. Fan, just a box. Set the fan speed with the table. Set the radiator as a porous region. Interface the regions, and then you're good to go. You'll be able to run. And you'll be simulating all of this. You can simulate not only, let me go back here. No, well, I don't want to. Not only will be simulating the flow around it, you'll be simulating how the radiator works and how the radiator affects all of that. And life will be good. Life will be good. Essentially, well, that's it. Have a great day, and thank you.